This lesson is called The First Day of Calculus. When you're watching this video, it is actually going to be the first day of calculus for you. This is Unit 2-1, the derivative. When you get into a car and you look at the dashboard, one of the things you're going to see is a speedometer, all right? Everyone has seen it. Now, when you ride in a car, does the speedometer always read the same? Okay? Speedometer obviously reads the speed of the car, but it is always reading exactly the same. And how long does it usually stay put? Could it possibly read 60 miles per hour at 2 p.m. and 80 miles per hour a minute later? What about half a minute later? What about half a second later? Okay, so this is where we're going to begin when we're talking about the speed of a vehicle. So what exactly does 60 miles per hour mean anyway? So you look down at the speedometer and it says 60. What does that mean? Well, if you keep going at that same exact speed for an hour, you'll have traveled 60 miles by the end of the hour. If you average that rate over the hour, you'll have traveled 60 miles by the end of the hour. So these are two ways of looking at what it means when the speedometer says 60 miles per hour. Well, now let's look at it in terms of calculus. What does 60 mean? So one way of looking at it is that 60 is the limit over shorter and shorter periods of time, okay, all starting at, say, 2 p.m., of the distance traveled divided by the time in which the traveling occurs, okay? So if you remember back to elementary physics, you learned that distance is equal to speed divided by time. So that's another way of looking at it in terms of calculus. So now let's say you're in a car and you don't have a speedometer. Or probably more likely, the speedometer doesn't work. It just doesn't register. So therefore, how can you determine what the car's speed is at, say, 2 p.m.? So let's say the speedometer doesn't work, but the odometer, which is right here, that works, okay? The speedometer stays at 0, but the odometer works. So could you find it using only the odometer and a watch? Could that give you the speed at, say, 2 p.m.? Now remember, okay, from physics, distance equals rate times time, or another way of looking at it is rate is equal to distance divided by time. Or another way of looking at it, instead of calling it rate, you could say speed is equal to distance traveled divided by the elapsed time. So let's look at an approximation as to how we could take and calculate this. So let's say we're looking for the speed at 2 o'clock, right? All right, the odometer works and we have a watch. Well, we could say, well, the distance at 2:05 that we traveled minus the distance at 2 o'clock that we traveled. In other words, the distance we traveled in those 5 minutes divided by 5 minutes. Well, that would give me an approximation of our speed at 2 o'clock. Well, that approximation isn't probably as accurate as we'd want. So let's make the time difference, the time interval even smaller. So let's say the distance between 2:02 and 2 o'clock. So that instead of being a 5-minute interval, we're talking a 2-minute interval. And so the speed at 2 o'clock is approximately equal to the difference in distance between 2:02 and 2 o'clock divided by 2. Now notice I didn't say equals. This is an approximation, all right? All right, so now let's look at a third approximation, and let's get that time interval down to, say, 1 minute. So we're looking at the distance it travels between 2:01 and 2 o'clock. And will that give us the speed? Or is that still an approximation? So does anybody see what we've been doing here? We're taking shorter and shorter time intervals starting at 2 o'clock, getting closer and closer to the true speed at 2 o'clock, which is what a speedometer actually says. So now let's take a giant leap forward here. And basically what we're doing here is we're taking a giant leap into calculus. And we can see that the smaller the time interval, delta t, okay? The smaller the time interval, the closer our approximation is likely to be to what the speed is at 2 o'clock. So how close can we get? In other words, what's the limit? Now, if you'll remember, in the first unit, we talked about limits, all right? So let's look at what we're trying to find and use what we know about limits. So we're going to say that the speed at 2 o'clock equals, now notice this is no longer an approximation, it equals the limit as delta t approaches 0 of the distance that 2 plus delta t minus 2 o'clock. So just a very small amount of time from 2 o'clock, the distance it travels between that small amount of time above 2 and 2 o'clock divided by that small amount of time, that's going to be the speed. And again, notice we're saying now that this is equals, okay? Now, why can't we just say that delta t equals 0? Well, delta t equals 0. If we plug in 0 here, this isn't going to work. So, but by definition, as this gets closer to 0, this is our definition of what the speed is at 2 o'clock. Now, what's the important point that you need to understand here? The limit formula that I just gave you is the definition of the derivative of the distance function d, or d of t. Let me repeat. The limit formula that I just gave you is the definition of the derivative of the distance function. Now, this definition isn't going to work just for distance. The calculus isn't just dealing with distance. It could also deal with populations of countries, bacteria cultures, electric charge, and even speed, okay? And the same goes for time as well. So it's not just for distance. It can be any of these things. That's what's so wonderful about calculus. All right, so let's go back to what we're talking about here. This whole lesson has built up to this point. The limit formula for derivatives. The derivative, okay, of a function, and this is the way we write it, f prime of x. That's the derivative of f of x. The derivative of f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h, okay? That's our definition. That's our limit definition for derivatives. Now let's see how we can use this in certain applications. Let's look at a couple examples here. We want to calculate the derivatives in each of these cases. So first I'm going to talk about example 1. What is the derivative of f of x is equal to 2x? So I have a function f of x equals 2x, and I want to know the derivative of f of x at x equals 3, okay? So first I want to find the derivative, then I want to find the actual value of that derivative at x equals 3. All right, so let's calculate it out here. First of all, I've got my function, f of x is equal to 2x. That's my function. All right, I'm using the definition. Remember, the definition is limit as h approaches 0 of f of x plus h minus f of x over h. Now, f of x plus h, I simply plug in x plus h for x in my function. So the function is 2 times x. Well, now it's going to be 2 times x plus h. Okay, so that is this portion right here. That's simply equal to 2 times x plus h. Minus f of x, well, f of x is simply equal to 2x. So that's 2x right here, divided by h. Well, let's simplify this. So distribute the 2. I get 2x plus 2h minus 2x over h. All right? Can I simplify it some more? So 2x cancels with 2x. 2h over h. The h's cancel. And I'm left with the limit of 2 as h approaches 0. Well, what's the limit of 2 as h approaches 0? It's simply equal to 2. All right? So the f prime of x is equal to 2. I could also write it as, you're going to see both of these methods. You're going to see either as dy dx or f prime of x. They mean the same thing. They mean the derivative of y with respect to x. Okay? So that's equal to 2. Well, I want to know, that's the derivative. So what is the derivative equal to at x equals 3? Well, if I plug in x equals 3, I get the derivative of the function at x equals 3 is simply equal to 2. All right, let's look at my other example here. My other example was f of x is now equal to x squared, okay? So that's my function. I want to find the derivative of f of x. I use the same definition, limit h approaches 0, f of x plus h minus f of x over h. So in place of x, I plug in x plus h. So now I've got x plus h squared minus x squared over h. I square that out and I get x squared plus 2xh plus h squared minus x squared. Again, my x squares cancel. I end up with 2xh plus h squared, okay? Now, I've got a h in all of these terms, so I can cancel this h out with that h and one of that h's. So what am I left with? I've left with the limit as h approaches 0 of 2x plus h. Well, as h approaches 0, I can substitute it here. So as h approaches 0, what is my answer equal to? It's simply equal to 2x. Again, I can refer to it either as dy dx or f prime of x, and this is equal to 2x. So the derivative of this function x squared is simply equal to 2x. Okay? So what's the derivative equal to at x equals 4? Well, I simply plug in 4 for 2 times x, and I get the derivative for x equals 4 is simply equal to 8. So this is a case where we've learned the definition for derivative, and we can use it in a lot of different cases. Eventually, however, we're going to learn the shortcuts to take in doing derivatives. But for now, let's use the definition until we really understand that, and then we can go on to the shortcuts.